So, very good evening and a very warm welcome to this live interaction session in the course Digital Signal Processing and its Applications. So, we are very happy to have participants already post some questions. I'm hoping the participants have also joined this chat so that we can discuss the questions in person, at least on a video call like this. Right, so I can see Amit Sinha has posted a question. Jnanendra has posted a question, and Supriya, I think, has posted a comment. Let me just check. So, okay. Yeah, so then I have, so is Amit Sinha in the call? I hope he's there in the call. Maybe he can respond on the chat. Anyway, the question which has been posed is, can an LTI system now, by the way, before I start responding to the questions, the whole purpose of this live interaction is that I have a one-to-one interaction with some of the participants of this course. I'm looking forward to some of you even posting questions during this chat, posting comments, questions, whatever it is during this chat, so that we can interact live and get a feeling of connecting between the instructor and the student. So I strongly encourage all participants to participate actively by posing questions, by sharing their thoughts about this course and so on, right? So with that little introduction to this session, let's begin. And let me start by answering. So if Amit Sinha is there in the chat, he can actually just confirm. Can we see the chat also here? We can just see, no, on here, no, we can see. So this chat is live now. Okay. So we'll wait for people to join. I guess people may join the chat. Isn't it? So is this showing the chat now? Okay. Okay, only Omkar is posted. Okay. So then let us begin by trying to answer. There are 7 viewers right now. So it's good. I mean, I would look forward to the viewers participating in this session, right? Now let us start by answering Amit Sinha's question. So his question is, can an LTI system be adaptively quantized to create a set that constitutes samples from individual or a combination of component systems? Okay, the LTI system. So example, he says if yn is equal to x1n plus x2n plus x3n, sample collected is x1 0 plus x2 0 plus and so on. Right. I think I understand what he's saying. You see, there are 2 aspects to this question. I'll take each of them and answer them one at a time. The first aspect is, as I understand it, but Amit, if he's in the chat, can respond. See, one part of the question is, can I have multiple inputs to a linear shift invariant system? I'm trying to interpret the question like that. Well, yes. I mean, in principle, you can have multiple inputs and also multiple outputs in a linear. So, you could have a linear shift invariant, multi-input, multi-output system. So that would be characterized by a collection of impulse responses. So in fact, an MIMO linear shift invariant system is perfectly conceivable. So which means it is linear shift invariant between any pair of input and output. Right? I think that is what is being alluded to here. Now, you could then characterize a system by a matrix of impulse responses. And in fact, then, each of those impulse responses would have, well, depending on whether it's a discrete system or a continuous, in this case, it will be a discrete system because we are talking about digital signal processing. So, so you would have a set of discrete systems, each occupying one place on that matrix, right? And each of them, each impulse response would have a Z transform, hopefully, which is the system function of that, that input-output relationship. So that means, when you have a multi-input, multi-output system, you have actually a collection of impulse responses, right, which characterize such a system completely. Okay. So anyway, we see, so the answer is yes. I mean, you can see what you're talking about, what Amit Sinha is talking about, is a special situation where you're actually giving as an input the sum of three inputs. So that means all those inputs would see the same system function. That's the way you want to look at it. All those inputs would see the same system function, right? On the other hand, they could also see different system functions. I mean, it's not that they have to see the same system function at the output. So it could be a multi-input but single output system, MISO system. That is perfectly a special case of the MIMO system, multi-input, multi-output system, right? So I hope I've clarified the question. If Amit Sinha is in the call, then he can make it clear whether that's what he wanted to ask or is there something else that he had in mind in addition, right? Now, you see, when you say an LT, also in the same question, I mean, if I understand correctly, there is a reference of quantization. Quantization is a different issue. You see, adaptively quantization is a different issue. Quantization really talks about numerical, you may say, inaccuracies or not being fully, fully able to deal with the numerical precision. That's a different issue. So I think probably what he means to say is, can an LTI system be adaptively configured to create a set and so on and so forth, right? Okay. So if Amit Sinha is in the call, I would invite him to answer, to post in the chat whether we have addressed his question correctly. Okay. Now let us take the next question by Jnanendra. Okay. Let's take the next question by Jnanendra. So the question is, if del t impulse signal is in continuous time, has undefined amplitude at t equal to 0, how can one express any arbitrary signal xt as a convolution of the signal itself with delta t? Very good question. You see, in fact, I would go a step further in this question. I would say, if the impulse, not undefined, the amplitude actually tends to infinity, but over an infinitesimal interval. So it's interesting. The impulse has an amplitude which goes to infinity, but over an infinitesimal interval. So what then is finite about the impulse? The area that it encloses. The area that the impulse encloses is finite, which means that when an impulse passes over the function, it captures the area at an instant. I mean, it sort of gets multiplied by the signal at that instant where the impulse is located. And the area of the impulse gets multiplied by that, so, and therefore, when you integrate, see, the action of an impulse is seen under the integral sign. So impulses are not functions. We are talking about continuous time impulses. Continuous time impulses are not functions. they are generalized functions. So, they are meaningful under an integral sign. They have no meaning. They have no meaning in the sense of traditional function. So, for example, talking about the amplitude of the impulse at a particular instant is meaningless. Or for that matter, it's not even a very good thing to say that the impulse, is zero outside the point at which it lies and so on. All these things are just crude ways of describing the impulse. That's the way I would look at it, right? So I would be inclined to say the impulse is a generalized function, and what is really known about the impulse, or what is measurable about the impulse, is the area that it encapsulates, right? And the area is finite, okay? Now, the question goes further to say if it is of undefined amplitude at t equal to 0. How can one express? So you see, it's not the amplitude which is coming into the picture when expressing an arbitrary function, right? It is essentially the area which is multiplied by the value of the function at a point where the impulse lies. So when you integrate, see, remember, you're expressing, now let us write the expression. So let us write the expression for writing. Let's write here. Now, how do you express a function in terms of the impulse? Let's write it down. Xt is integrate overall. Now, what are we saying here? You see, one way of understanding this is you take the function xt. Now, in fact, you could see here, let us consider a symmetric impulse. So let's say the impulse starts from a symmetric function. So you don't have to worry about t minus tau or tau minus t, right? So it starts with a symmetric pulse, which takes the height of 1 by delta over a width of delta. Okay, and symmetric. So delta t minus tau and delta tau minus t are the same. So what are we writing here? We are saying we have xt, this is xt, what we have drawn here, x, which I'm writing in terms of the variable tau. And you have this impulse, which is located at tau equal to t. Okay, so you have this pulse. First, let's begin with the pulse, which has a height of 1 by delta and a width of delta. Okay, so what have we done? We have multiplied x tau by this small pulse, which has a height of 1 by delta and a width of delta, and is centered around tau equal to t. So essentially, as delta goes smaller and smaller, as delta tends to 0, the area encapsulated becomes x, you see, xt into delta into 1 by delta. Is that right? So which is x of t. That's what we are saying. When you multiply x tau by this very, you may say, very narrow impulse, which is located at tau equal to t, and continues to encapsulate the area of 1, no matter how small delta is, then you're essentially saying the impulse or the pulse which goes towards an impulse picks up the value of x tau at tau equal to t. That's the way you should understand. I hope that is clear. Okay. All right. Now let's take the second question. The second question is, if 1 by 4 sinc multiplied by sinc n by 4 is not absolutely summable, how can it have a frequency response like an ideal low-pass filter with finite amplitude? It's a very good question. This is a question by Jnanendra. So you see, he's asking if 1 by 4 sinc, that is correct, sinc n by 4 is not absolutely summable. So you see, the contradiction seems to be, or seems to come out in the fact that the impulse response is not absolutely summable, yet it seems to have a frequency response. So, I mean, it is a moot point whether the impulse response needs to be absolutely summable for it to have a Fourier transform. That's a very interesting question. You see, this is one of those, kind of tricky points about the discrete time Fourier transform. Actually, there is a singularity in the Z transform of this impulse response. There's a singularity at Z equal to 1, right? In fact, so the situation is like this. The discrete time Fourier transform here is defined for several points on the unit circle. And that's why you have a frequency response. But there are situations like this ideal low-pass filter, which is unstable, but where there's still, so the confusion comes. I can very well understand the confusion. The confusion comes from the fact that you would imagine that since the ideal low-pass filter is unstable, the unit circle should not be in the region of convergence of the Z transform. So how come we have a frequency response? It's a very good question. Well, here you have to broaden your definition of the discrete time Fourier transform. You say that you are willing to accept the discrete time Fourier transform on points of the unit circle where that summation converges. So it's interesting, it's an example of a discontinuous function on the unit circle. See, let's understand this clearly. So, in fact, let's take a simpler situation. You have u of n, the unit step. The unit step as such is not absolutely summable. That's obvious. Yet, people attribute a discrete time Fourier transform to the unit step. They say that the dtft in the limit can be seen to be 1 by 1 minus e raised to the power minus j omega. So tongue in cheek, as they say. This is the DTF. Now, here the unit step is not absolutely summable. So when you try to calculate this sum, you try to calculate this sum, un z to the power minus n, summed over all n, which is, you try to calculate Z transform, it would be summation n going from 0 to infinity z to the power minus n. And then, you would say, well, it is equal to 1 by 1 minus z inverse. But then mod z should be greater than 1. I mean, sorry, mod z should be less than 1. Sorry, mod z to be greater than 1 here, because, yeah, that's right. Mod z greater than 1. Is that right? Because you want it to be outside to the exterior of the unit circle. So actually, unit circle is not included. So what are we saying? How can you attribute a DTFT to it? Well, the situation is like this. If you look at the Z domain here, and you look at the unit circle, the singularity is here. So when you try to integrate, when you try to integrate for the DTFT, how do you integrate for the DTFT? You see, when you put z equal to e raised to the power j omega, what you're doing is you're actually using an integral which takes a small, detour at the point of singularity. So you integrate that way. When you are integrating along that contour, see, you are allowed to integrate on any contour which is in the region of convergence. So here, the singularity is not in the region of convergence. But, you can play this trick of making your contour slightly deviate off the singularity at z equal to 1. So that is, you may call it a cleaved integral. And that's how you define the DTFT, which is notionally correct at all points other than z equal to 1. So we say in the limit, the DTFT looks like that. A similar idea has to be used when you're talking about this kind of a discontinuous discrete time Fourier transform, which is evident in the low pass filter. That's a very good question, actually. See, if it's not absolutely summable, then it would appear that the unit circle is not in the region of convergence. But you have to play this trick of using the generalized idea of integration by moving around the point of singularity and so on and so forth, right? So it's a bit of an advanced idea in complex analysis, but I'm glad that Jnanendra has raised this question. Well, I won't take this discussion too far. I've given you an indication of how to deal with this, right? But let's come back to if there are more questions in the chat. Yeah. Let's see if there are more questions in the chat. Yeah, thank you so much. So there is there seems to be, a comment from Supriya V. And, she says, good teaching and explanation. So I'm so glad that Supriya found the teaching and explanation worthwhile. I'm very glad. If she has any other questions, then go there. Are there any other questions? There are 5 viewers. So you're very welcome to post your questions. You can share any thoughts that you have. Right? I'm here to. Please feel free to post your questions so I can respond to them in the chat. maybe the people who are in the chat right now can introduce themselves. I see 4 concurrent viewers. Yes, good evening, Sri Ramulu. Yes, good evening, Sri Ramulu. Please go ahead. I would love to hear your question or comment. Oh, you're Jnanendra. Okay. Did you understand my response to your question? I know it's a slightly, you understand my response to your question? If you can take the discussion further on the question that you've asked. Maybe I'll sort of, explain a little more since you're in the chat. I'll explain a little more. Share this screen again. Since Jnanendra is in the chat, let me try to explain a little better, a little more on his second question. That's more difficult. So you see the cleaved integral. Let's explain that. Now, how would you essentially, you have u of z, capital U of z, the z transform of un, which is 1 by 1 minus z inverse. Now, suppose you write the inverse z transform. You're trying to write the inverse z transform. The inverse z transform is 1 by 1 minus z inverse, okay, z to the power n minus 1 dz over a contour in the region of convergence. Now, what you do is, that's what I was mentioning. When you take this contour here, So you have the Z plane here. You have a singularity here at Z equal to 1. And the contour that you choose is like this. You need to choose it in the region of convergence. The region of convergence is mod Z greater than 1, right? So you choose a contour which starts approaching almost at the unit circle, right? Almost at the unit circle. But here you cleave the contour a little bit. Make a very small circle with infinitesimal radius around Z equal to 1. Continue that. This is the contour that you use. Almost the unit circle, right? That's the contour that you use to invert the Z transform when you want to invert the DTFT. So when you say you're putting Z equal to 1, Z equal to e raised to power j omega, essentially you're saying you're assuming that the DTFT exists and you're omitting the point Z equal to 1. Now to justify the inverse DTFT, you're saying cleave the contour at Z equal to 1. Now, in fact, it's interesting. If you look at the impulse response, of the low pass, of the ideal low pass filter, it has, as he says, as Jnanendra says, it has the form some sine omega Cn by pi n, isn't it? For n not equal to 0, and of course omega C by pi for n equal to 0. Now, let's take a specific case to give an example. Let's take omega C equal to pi by 2, I'm sorry. So you get sine pi by 2n by pi n for n not equal to 0 and half for n equal to 0. Now you can write down, you can in fact write down this sequence. So sine pi by 2n, you see, for all odd integers, we'll take alternating signs plus minus 1. And for even integers, it would take the sign, it would essentially be 0, right? Because sine for multiple of pi. So this would be half for n equal to 0. Yeah, I'm very happy to see that Jansi has, yeah, he has introduced himself, or she, and she has taken the subject as coursework for PhD. Very good, Jansi. I'm very happy to see that. I'm also very happy to welcome Amit Ranjan, whose question I just answered a little while ago. Did you see my answer, Amit? Please respond in the chat. Do you see my answer to your question? Yeah. Now it's half for n equal to 0 and minus 1 to the power, well, n by 2. So, so it's n minus 1 by 2, right? For n not equal to 0 and n odd by pi n. And 0 for even n. Right? Now, if you look at the sequence, and if you happen to construct its Z transform, so its Z transform has a relation you can write in terms of log natural 1 minus z inverse, or log natural 1 minus z. And in fact, log natural 1 minus z inverse and log natural 1 minus z are not, of course, they're not rational. That's why you know that this is an irrational system. Its Z transform is not rational. Further, there is a problem with region of convergence. You see, in fact, it's log natural 1 minus Z inverse. That part has a convergence in one part of the Z plane, the other one has a convergence in the other part of the Z plane. And the only intersection for those two parts is on the unit circle. That's interesting. So on the unit circle, you can evaluate this, but beyond that, only one part of the sequence can be evaluated. Either the right part of the sequence for n greater than or equal to 0, I mean, only that part of the Z transform converges, or only the left. So, it converges. A part of the Z transform converges for mod Z greater than 1, and the remaining part converges for mod Z less than 1. So, it's a peculiar situation. There's a very thin intersection. And on that intersection, you need to do away with that singularity. It's a very funny situation because, all this comes because you're dealing with a discontinuous discrete time Fourier transform. You're dealing with a discontinuous discrete time Fourier transform. So the whole situation of how you calculate the Z transform, its region of convergence, has to be dealt with differently, right? So I've tried to answer, it's a profound question. I'm glad that somebody raised it. Right? So, Gyanendra, have you understood, at least somewhat understood what I'm trying to explain to you? And Amit Ranjan, did you see my response to your question? Your question, I'll take it up again. This is the question asked by Amit Ranjan. So, you see, you can have multi-input, multi-output systems. LTI, LSI systems. Right? So, there you have a set of outputs. You can call them Y1T up to Y, or, let's take the discrete case. Y1n up to Ymn as a function. So, here it's, it would be essentially summation. So, you have a vector of outputs related to a vector of input. So it would look something like this. You would say YL of n is summation, let's say k going from minus to plus infinity. And in fact, you also need to sum over another index. Let's call that m. M going from 1 to n. H, L, M. K, X, M, N minus. So here we are talking about n inputs, x1 to xn, and m outputs, y1 to yn. And you can have nm impulse responses like this. So this is what is called a multi-input, multi-output system, MIMO system. So is the response to your question clear, Amit Ranjan? Also, Jansi, would you like to ask any questions? You're doing this work course for your PhD. So would you like to ask any questions? Nyanendra, any other questions? Please respond in the chat. If there are any other people in the chat, they are very welcome to respond. Are there any other questions? I hope this course is helping you in your PhD, Jansi. So, Amit, anybody else in the chat? Can you tell us whether anything else needs to be discussed? Amit Ranjan, Jansi, Jnanendra, anybody else in the chat? Okay, I see a question from Jnanendra. Can we apply I inverse GTFT for a sequence that has Z transfer form, this Z transform with a region of convergence? If we can apply, what role does ROC play? Okay. See, actually, you can invert the Z transform only in the region of convergence. Now, you see what is happening when in the discrete ideal discrete low pass filter, the sequence on the right side of n equal to 0, for n greater than equal to 0, has a Z transform which converges in one part. And the sequence on the left side has a Z transform which converges in another part. Now, on the unit circle, these two parts meet at the unit circle. And there's an essential singularity at Z equal to 1. So strictly speaking, you can only invert for the right part of the sequence for mod Z greater than 1, and for the left part of the sequence for mod Z less than 1. So you have to think of it as two parts of the sequence, each of which has a Z transform. And when you formally add it, I will show you again. So when you formally add it, I'll have to start sharing again, right? So when you formally add it, okay, See, you get log natural 1 minus Z inverse and log natural 1 minus Z for the right and the left parts of the sequence. So when you add it, what happens is, you would get, you would essentially get an intersection of the two regions of convergence, or rather, not even an intersection. The boundaries of both the regions of convergence are the unit circle. So what you do cleverly is you invert the Z transform for the left part for n less than 0 by looking inside the unit circle. You invert it inside the unit circle by cleaving around Z equal to 1. And you invert it for n greater than 0 by looking outside the region of outside the unit circle and cleaving again at Z equal to 1. So it's a process where you invert the sequence for n greater than 0 with a separate strategy and for n less than 0 with a separate strategy. So that is the idea of using the region of convergence. In fact, in that sense, there is no intersection between those two regions of convergence. So you have to think of it as a sum of two sequences, each of which has a Z transform with a region of convergence. That's the way. And the two intersect, or the two regions of convergence have a common boundary, namely the unit circle. So you can invert each part of the sequence, but you cannot invert one expression for the whole sequence. That's the way you should understand it. Am I getting across, Jnanendra? And, that's, in some sense, it's on that unit circle, this discrete time Fourier transform is discontinuous for the ideal filter. Yanindra, have I got across to you? Any other questions, Amit or Jansi or Gyanendra? Okay, so Gyanendra has confirmed. Amit, are you also in the call? And Jansi? So we have about 5 minutes more for this interaction session. Anything more that you would like me to talk about in this interaction session? Okay, if I don't see any more questions in this session or any other comments, so then maybe we can close the session, this interaction session. And we would like to have another interaction session. We had planned one on 27th if on Thursday, if you have a lot of questions today, but I don't see any further. Whatever questions were there today, we've addressed them. So I don't think there's a point in having a session immediately on the current Thursday, but we'll have another interaction session after a couple of weeks, after some time, during which time you can post more questions or any comments or anything that you would like to talk about during the interactive session. So we'll then conclude this session and we look forward to meeting you again. After a couple of weeks or more, right? Because we addressed most of the questions today.